Hey everyone, welcome back. So today what we want to do is study what are called improper integrals. And here's the idea. What we'd like to do is we'd like to take integrals and see what happens as the interval of integration gets larger and larger and larger. Right? So that's called an improper integral. So let's start off with a definition here. So for each little t greater than or equal to some a, right? So fix some constant a, and we want to look at all possible t's greater than or equal to a. I want to define a function, let's call it capital A of t, and it will be equal to the integral from little a to t of f of x dx. So let's draw the picture here. We've got some function. Let's say this is y equals f of x. A is over here. And so now we say for each t greater than a, we define this formula right here. So we've created a function, capital A. And how is it computed? Right? How do you compute capital A of little t? Well, you take some value t greater than or equal to a, and a of t is the integral, and so I called it capital A for a reason. Capital A of t represents the area under the graph over the interval from a to t. So a of capital T is the area of that shaded region right there in my picture. Now we've said for each t greater than or equal to a. So we can choose any t we like, and we can allow, so let's say I choose a new t, right? Then a of t represents all of this area. And I can extend this picture, and instead I can say, oh, actually I want to choose my t way out here. Okay, so now a of t represents that entire area right there. And so this leads to a question. The question is, what happens to a of t as t gets larger and larger and larger? What happens as t goes to infinity? And so that's going to lead to this next definition, and this kind of long-winded definition, so you just have to bear with it. These are called type 1 improper integrals. And there's three parts to this definition. The first part, so for f of x continuous on the interval from a to infinity, closed interval, closed a, open of course at infinity. Yeah, so we're going to define integral from little a, and now this is the first time that we've seen this. Instead of an actual number here, we're putting the symbol infinity. So we're going to define the integral from a to infinity of f of x dx. By definition, this is the limit as t goes to infinity, integral from a to t f of x dx. So this is called an improper integral, right? Anytime if we have a limit of infinity right here, this is called an improper integral. And notice this is a limit now. And so this limit may or may not exist, right? If the limit exists, then we say it's convergent. Otherwise, we say it's divergent. I'll write this down once I finish the entire definition, but here's part A. We define, when you see this symbol right here, integral from a to infinity, you immediately replace it with this limit. Okay, part B, for f of x continuous on the interval, now it's going to go from minus infinity to a. Define the integral from minus infinity to little a of f of x dx. This will be the limit as t approaches minus infinity. Integral from t to a f of x dx. Right, so once again, this is called an improper integral, type 1 improper integral, and anytime if you have a limit of minus infinity, you immediately rewrite it as a limit. And then there's part C of the definition, and that's going to be the situation where we have infinity for the top limit of integration and minus infinity for the bottom. So part C for f of x continuous on all real numbers now, so from minus infinity to positive infinity, define the integral from minus infinity to positive infinity, f of x dx. What we're going to do is we're going to write it as one of these plus one of these. So it will be integral from minus infinity to a f of x dx plus, unfortunately, I'm going to have to erase this portion right here, plus integral from a to infinity f of x dx. So what we did, or what we do when we have a minus infinity to positive infinity, we rewrite it as an integral from part A plus an integral from part B. And it doesn't matter which a I choose right here. I can choose any real number a. Typically, I just choose 0. So yeah, usually I write 0 there. So so when the limit exists, the improper integral is convergent. Otherwise, divergent. So that will be the question when we're given an improper integral. Is this improper integral convergent or is it divergent? How do you answer that question? Well, you rewrite it as a limit in the first two cases. In the third case, in part C, rewrite it as the sum of these two integrals and then compute both of these. Right? If both limits exist, then you say it's convergent and it converges to the sum of those two integrals. Okay, so let's look at some examples now. So first example, let's look at the integral from 1 to infinity of 1 over x dx. Here we've got an improper integral. We rewrite it as a limit. So this is limit as t goes to infinity, integral from 1 to t, 1 over x dx. And now we compute the antiderivative as we normally would. This is equal to the limit as t goes to infinity. The antiderivative is natural log absolute value of x, and we evaluate from 1 to t. Plug in the limits of integration, and what we get is limit as t goes to infinity. This will be a natural log of t. It'll be minus natural log of 1, which is just 0. So this is limit as t goes to infinity, natural log of t. Notice that I dropped the absolute values. As t goes to infinity, t is definitely positive, so the absolute value of t will just be t. As t goes to infinity, natural log of t equals infinity. And so what we have is this improper integral is divergent, right? Its limit does not exist. It's equal to infinity. There's a picture that goes along with this. Let me put the picture right over here. Right, the graph y equals 1 over x looks like that. And so this question right here, this improper integral, is asking how much stuff, what is the area below the graph of 1 over x as you go from 1 and you keep going out to infinity. And it turns out that there's an infinite amount of area, an infinite amount of stuff under that graph right there. Okay, so next example. Let's look at the integral from 1 to infinity of 1 over x squared dx. So it's similar, right? I mean, our limits of integration are the same, but we changed our integrand slightly. Instead of 1 over x, we have 1 over x squared. Remember, when you have an improper integral like this, you rewrite it as a limit. So we have limit t goes to infinity, integral from 1 to t. This is a 1 over x squared dx. Now I compute the antiderivative as usual. So we will have, this is a negative 1 over x, and we evaluate from 1 to t. Now plug in the limits of integration, and so we'll have a limit as t goes to infinity, negative 1 over t plus 1. And as t goes to infinity, 1 over t is approaching 0, and so this limit is equal to 1. That tells us then that this improper integral is convergent. Right? We got an actual number. And the picture that goes along with this one, if you look at the graph of 1 over x squared, it looks very similar. But as x gets larger and larger and larger, this portion of the graph squeezes down closer and closer to the x-axis much faster than this one does. And so it turns out we got infinity for the area under this curve. We got 1 right there. If you took all of that area and tried to arrange it, you could fit it into a box, right, whose side length is equal to 1. Right? So divergent in the first case because we got infinity. When you get a number, we say that it's convergent. This improper integral converges to 1. The interpretation geometrically, there is a finite amount of stuff under that graph right there. Its area is exactly equal to 1. Okay. So next example, let's look at this one here. Integral from minus infinity to positive infinity. 1 over 1 plus x squared dx. Now remember, what we do is we rewrite this. This would be minus infinity. I like to choose a equal to 0, so it would be minus infinity to 0 of 1 over 1 plus x squared dx plus integral 0 to infinity 1 over 1 plus x squared dx. And so now we need to compute each of these individually, see what we get, right? If either one of them diverges, we can stop and say that the original one is divergent. If they both converge, we're going to get a number here, we get a number here, add those two numbers together, that tells us what this one converges to. So I'm going to do this one right here first. So let's look at integral from 0 to infinity, 1 over 1 plus x squared dx. Remember, the first step is to rewrite this as a limit. So this is limit as t goes to infinity, integral 0 to t, 1 over 1 plus x squared dx. Now compute the antiderivative. So that's limit as t goes to infinity. This will be an arctan x, and we're going from 0 to t. Now plug in the limits of integration, so we have limit as t goes to infinity, arctan of t minus arctan of 0, and arctan of 0 is equal to 0. And remember, when we talked about graphs of inverse trig functions, I said the only one that I actually care about is arctan. You need to know the graph of arctan. As t goes to infinity, arctan of t, remember arctan has a horizontal asymptote, right? It's equal to pi over 2. So that limit is equal to pi over 2. You can check, so we just showed that this one converges to pi over 2. It turns out that this one does also. And so in the end, so let's say it like this. So it'd be good exercise for you. So check integral from minus infinity to 0 of 1 over 1 plus x squared dx equals pi over 2 also. So our conclusion then, integral from minus infinity to infinity of 1 over 1 plus x squared dx, it converges pi. And the picture goes like this. The graph of 1 over 1 plus x squared looks something like that. So it's symmetric on the left and the left-hand side and the right-hand side are matches. So this side, the right-hand side, has area pi over 2 under the graph. Area on this side is also pi over 2. Add them together. When you get pi. Oh, yeah, that's the graph y equals 1 over 1 plus x squared. Let's do another example. So now we're going to do integral from 2 to infinity of 2 over x squared minus 1 dx. Remember, we first rewrite this as a limit, so we have limit as t goes to infinity. Integral from 2 to t, 2 over x squared minus 1 dx. Okay, so now we've got an integral. We need to compute this integral, or compute the antiderivative. We need to think back to our methods of computing integrals like this. This is a partial fractions, right? It's a polynomial over polynomial. And so if you go through the process, what you'll get, oops, that should be a t, is that this is 1 over x minus 1 minus 1 over x plus 1 dx. Let me make sure I did that right. There'd be an x plus 1 minus that. Yeah, right. So from here to here, what I did was partial fractions. Okay, now we can compute the antiderivative, so this becomes limit as t goes to infinity, natural log absolute value x minus 1 minus natural log absolute value x plus 1, and we're going to go from 2 to t. Let's see, before I plug in before I compute the limit, or actually before I even plug in the limits of integration, I'd like to simplify this using rules of log. So this is equal to limit as t goes to infinity, natural log absolute value x minus 1 over x plus 1, and we're going from 2 to t. Now let's plug in the limits of integration. This becomes limit as t goes to infinity, natural log of, let's see, this will be a t minus 1 over t plus 1. Fine. You can leave absolute values there, I guess. And then we subtract natural log of, when I plug a 2 in here, I'm going to get a 1 in the top and a 3 in the bottom. So it'll be natural log of 1/3. Now, as t goes to infinity, inside the absolute values, that's approaching, right? So this stuff right here is approaching 1. So natural log of 1 is 0. And so this part is 0. So what we got is negative natural log of 1/3, which is the same as natural log of 3. So conclusion, this integral right here is convergent. It converges to natural log of 3. So if you think about the first two examples I did integral from 1 to infinity of 1 over x, and then I did integral from 1 to infinity of 1 over x squared. The first one diverged, the second one converged. So, right, we're doing integrands, right, first a 1 over x, then a 1 over x squared. And you can ask the question now, what happens as you vary that, that exponent right there? Clearly we get convergent sometimes and divergent sometimes. So, or divergent other times. So let's find out what the cutoff is. So let's consider the integral Let's just do 1 to infinity of 1 over x raised to the pth power dx. We know that it diverges in one particular case when p equals 1. So let's assume p not equal to 1, because we already know the answer there. We also know it for 2, but 1 somehow is a special case. So if we rewrite this as a limit, so this is limit as t goes to infinity, integral from 1 to t, let's write that as x to the minus p dx, and then compute the antiderivative. Let's see, that's going to be limit as t goes to infinity, x to the 1 minus p divided by 1 minus p, and we go from 1 to t. Now let's plug in the limits of integration. So this is going to be limit as t goes to infinity, t to the 1 minus p over 1 minus p minus, if I plug in a 1, I'll have a 1 over 1 minus p. Okay, so there's the answer. And notice we've assumed that p is not equal to 1, and part of the reason is I wanted to be able to compute the antiderivative and not be divided by 0, right? I didn't want to do that special case. So now, as t goes to infinity, what's going to happen? Well, now we only care about that portion right there. And so let's consider two cases. If p is larger than 1, that will make this exponent negative. If this exponent is negative, then you can think of, right, a negative exponent pushes that t down in the denominator. So as t gets large, this is going to approach 0. So when p is greater than 1, negative exponent means that this limit will equal 0. If p is less than 1, then we'll have a positive exponent, and so as t goes to infinity, our numerator is going to go to infinity, which will give us infinity. So that tells us then that this integral right here, this improper integral, is convergent whenever p is greater than 1, and it's divergent when p is less than or equal to 1. And so that leads us to a theorem called the p-test, and it goes like this, integral, and I did this with a 1. It really doesn't matter what number I have here as long as it's greater than 0. So let's write it like this, integral from a to infinity, 1 over x to the p dx converges if p is strictly greater than 1 and diverges if p is less than or equal to 1. So now we can use this in any situation. If the problem says determine whether this improper integral converges or diverges, and it's of that form, we don't need to rewrite it as a limit and compute it. We can just use this fact right here. So for example, integral from 3 to infinity of 1 over x raised to the 1.01 dx. This converges. And all I need to do is say how I know this. I know this because p equals 1.01, which is greater than 1. All right, so it makes it quicker. I don't need to compute the limit. We've checked this for all possible values of p now. Now, there are times when you get an integral, an improper integral, and the process of finding the antiderivative is actually impossible or extremely difficult. But if you just want to know whether it's convergent or divergent, we're going to have a way that will allow us to decide that. And this is called the comparison test. Or I think your book says comparison theorem, but I'm just in the habit of calling it comparison test, so that's what I'm going to call it. So comparison test. And so it goes like this. So let's let f of x and g of x be continuous on the interval from a to infinity. There's two parts to the comparison test. Oops, I need to say one more thing. Where 0 less than or equal to g of x less than or equal to f of x. Right, so let's draw the picture and then we'll write down the conclusion here. So we've got a couple of continuous functions. Here's the graph y equals f of x. Here's the graph y equals g of x. And we know that it's continuous on the interval from a to infinity. So part A, if the integral from a to infinity of f of x dx is convergent. So what is that saying then? It's saying as you go from a to infinity, the amount of stuff under the bigger graph is finite, right? There's a finite amount of area. Well, if there's a finite amount of area under the f of x graph, the bigger graph, then there's got to be a finite amount of area under the smaller graph also. So if this is convergent, then integral from a to infinity g of x dx is convergent. So there's part A, and then part B is going to be kind of the reverse. So if integral from a to infinity g of x dx is divergent. So now we know that there's an infinite amount of area under the smaller graph. If there's an infinite amount of area under the smaller graph, then there's got to be an infinite amount under the larger graph. So if this is divergent, then integral from a to infinity f of x dx is divergent. So let's see this one in action now. What this will allow us to do is to determine whether certain functions, for which we can't even figure out how to integrate, actually give us a convergent or divergent improper integral. So first example, let's look at the integral from 1 to infinity cosine squared x over, where'd it go? Oh, over x squared dx. So here's what I want to do, is I want to notice that if we look at cosine squared x over x squared, that is less than or equal to 1 over x squared. Why is that? Well, we know that cosine stays between plus and minus 1, which means that cosine squared is between 0 and 1. Now, of course, someone out there, okay, good, that's another horn. Okay, sorry. So this inequality is true. And then we can say, since integral from 1 to infinity of 1 over x squared dx is convergent. How do I know that? Well, by the p-test. P equal 2 so is integral from 1 to infinity cosine squared x over x squared dx by the comparison test. We showed that our integrand is smaller than one that we know converges. So ours has to converge. And notice, I have no idea how to integrate this. This would be a nightmare. In fact, I don't think there is a nice formula, or there is a formula. There is no formula for figuring out how to integrate this. I mean, you could try integration by parts, but I don't even think it works. I think it makes a mess. So the point is, we were able to show that this is convergent just by applying the comparison test and showing that our integrand is smaller than one that we know converges. So another example, let's look at integral from 2 to infinity, 1 over x to the 5th plus 3x plus 1 dx. I absolutely do not want to have to integrate this, so I don't want to have to decide whether it's convergent or divergent directly. Instead, what I want to use is the comparison test, and what we want to do is focus on the dominating term. in this case, I've got an x to the fifth in the denominator. And that is really what I did in the last example. I noticed that our dominating term there is x squared, and so the idea is that this integral right here will behave essentially like a 1 over x squared. Same thing here, even though I've got this extra stuff here, this one is going to behave just like a 1 over x to the fifth. That's the idea. So now let's write down our inequality, which when you apply the comparison test, you need to write down an inequality and then a concluding sentence. So what do we have? 0 greater than or equal to x to the fifth plus 3x plus 1 less than or equal to 1 over x to the fifth. Now, you need to write down a true inequality. Why is this true? Well, if you look at the denominator here versus here, when you make a denominator larger, you make the fraction smaller. So this fraction here is smaller than this one because it's got a larger denominator. Then we write down our concluding sentence. So since integral from 2 to infinity, 1 over x to the fifth dx converges, using the p-test where p is equal to 5, so does integral from 2 to infinity, 1 over x to the fifth plus 3x plus 1 dx by comparison test. Okay, let's try one more example of that. So let's look at integral from 5 to infinity, 1 over square root x squared minus 1. Now, when you apply the comparison test, you kind of got to have an idea of whether it's going to converge or diverge, because you need to decide whether you're going to use part A or part B of the comparison test. So in this case, I looked at it, I said, this is going to behave like a 1 over x to the fifth, which means it's going to converge. So I want to make my integrand smaller than something I know converges. But if you're going to use part B, you need to make things go the opposite direction. So when I look at this integral right here, I say, okay, dominating terms. I've got a 1 in the numerator. I have an x squared under the square root. This one is going to behave like a 1 over x, which means that we suspect that it's going to diverge. And so to set this up, we say, all right, well, let's look at this. Here's my inequality. Now, why is this true? If you subtract in a denominator, you make it smaller. If you make the denominator smaller, you make the overall fraction larger. So what we have, this fraction is larger than this fraction because the denominator on the right-hand side is smaller. Once we have a true inequality, then we can say since integral from 5 to infinity of 1 over x dx diverges, once again by the p-test, here p equals 1, so does our original one. By the comparison test, we showed that our integrand is larger than one that is known to diverge. The improper integrals that we're working with so far, those were called the type 1 improper integrals. There's also type 2. So let's get to those now. And the definition, once again, will be a little bit long-winded. All right, so we're going to look at type 2 improper integrals. And so part A, let's let f of x be continuous on the interval. It's going to be half open. right? So it's going to be continuous on the half open integral from a to b, open at a, closed at b, but discontinuous at a. Think asymptote, vertical asymptote, right? So when you have vertical asymptote, it'll be continuous on a certain portion, right? But discontinuous at that spot where the asymptote occurs. So it's continuous here, discontinuous there. Then when we look at the integral from a to b, if you have a discontinuity at the lower limit of integration, that's an improper integral. And so you need to rewrite this as a limit as t approaches a from the positive side, integral from t to b f of x dx. Part B. Now we're going to just have the discontinuity occur at the other side. So this will be let f of x be continuous on the interval. Now it'll be closed at a, open at b, but discontinuous at b. Then, integral from a to b, if you've got a discontinuity at the upper limit, that's an improper integral. And so you have to rewrite that as a limit as t approaches b from the negative side, f of x, integral from a to t f of x dx. Then there's part C. If f of x is continuous on the closed interval excuse me, from a to b, except at some point C in between A and B. Then the integral from A to B is improper because it's got a discontinuity in between the two limits. And so what do we do here? We write it as the sum of two improper integrals, integral from A to C, f of x dx, plus integral from C to B, f of x dx. Compute each of these improper integrals individually. If you get numbers for each of them, add them together, the original one converges to that number. Otherwise, if one of them is, as soon as you see that one of them is divergent, you can just stop and say that the original is divergent. So I guess I need to finish off this definition. So if the limit exists, then the improper integral is convergent. Otherwise, divergent. Okay, so let's look at a few examples here. First example, integral from 0 to 1 over x dx. So notice this integrand is continuous on 0 to 1 except at 0. So we have a vertical asymptote at the lower limit of integration. That means we've got an improper integral. So we need to rewrite that limit as t approaches 0 from the positive side. Integral from t to 1 over x dx. Now compute the antiderivative as usual. So this is limit t approaches 0 from the positive side. Natural log absolute value x. We go from t to 1. So that's equal to, let's see, when I plug in the limits of integration, well, let's write it out here. Limit as t goes to 0 from the positive side, natural log of 1 minus natural log of t. That part's equal to 0. Now, as t approaches 0, remember the graph of the natural log goes like that. It approaches negative infinity. So it's going to be minus negative infinity. That limit is equal to infinity. So this improper integral diverges. And the geometric picture, now we're looking at the area below the graph between the asymptote and 1, right? And it tells us that there's an infinite amount of area underneath. Okay, so next example, let's look at integral from -1 to +1, 1 over x squared dx. Okay, so now you've got to remember to notice this. It's not discontinuous at either of the endpoints, but it is discontinuous right in the middle. So if there's a discontinuity between the limits of integration, you've got an improper integral. So I need to write this as -1 to 0. All right, we've got the discontinuity at 0 now, so -1 to 0, 1 over x squared dx, plus 0 to 1, 1 over x squared dx. So I'm going to do this, the second one here. So integral from 0 to 1, 1 over x squared dx. Rewrite, oh, excuse me, rewrite, I got the hiccups now. Integral from, as t goes to 0 from the negative side, no, from the positive side. Integral t to 1, 1 over x squared dx. That's equal to, now I can compute the antiderivative, so that's equal to limit as t goes to 0 from the positive side, -1 over x, and we're going from t to 1. That's equal to limit as t goes to 0 from the positive side. So it'll be a -1 plus 1 over t. And as t approaches 0, that is approaching infinity. That tells us that this first piece, this one right here, is divergent. So we can stop right here. Right? As soon as we know that one of them is divergent, the entire improper integral is divergent, and so this is divergent. Okay, one more example. Integral from 0 to 1, natural log of x dx. This is improper because natural log has a vertical asymptote at 0. So I need to rewrite this as a limit as t approaches 0 from the positive side, integral natural log of x dx. And we're going, sorry, from t to 1. Now, let's see, now we need to remember how to integrate, right? How to find the antiderivative of natural log. You might remember that from a few, excuse me, I'm sorry. Got the hiccups bad now. You do integration by parts here. So we will let u equal natural log of x, dv equals dx, du is 1 over x dx, and v equals x. So this becomes limit as t goes to 0 0 from the positive side. And now I'm going to do the result. I'm going to write down the result of integration by parts. So it's going to be u times v is an x natural log of x. And then we'll have minus the integral, and I need my limits here, from t to 1 minus integral of v du. So v times du, that'll just give us a dx. So this will be a t to 1 dx. Let's get that last integral out of the way. So this is limit t goes to 0, x natural log of x, evaluate from t to 1, minus, this is an x going from t to 1. So that's equal to limit as t goes to 0. When I plug a 1 in, I'm going to have 1 times natural log of 1, which is 0. And then it'll be a minus t natural log of t. Minus, now when I plug in that, I'll get a minus 1. And then it'll be plus t. As t goes to 0, right, of course, t goes to 0. So now what we need to do is figure out what this limit is as t goes to 0 of t natural log of t. That's an indeterminate form, right? As t goes to 0, we're going to get 0 here, we're going to get a minus infinity right here. So let's just off to the side, let's compute limit as t goes to 0 from the positive side of negative t natural log of t. Right? And you should believe, right, this is 0 times minus infinity, so it's indeterminate. So I can rewrite this by dividing by the reciprocal. This will be a natural log of t, negative natural log of t divided by 1 over t. Now we've got an infinity over infinity, so I can apply L'Hopital's rule. So this will be limit as t goes to 0, negative 1 over t divided by negative 1 over t squared. So I just took the derivative of the top and the derivative of the bottom. Simplify, and we get limit as t goes to 0. Well, it'll just be a positive t. That limit's equal to 0. Which means that piece is approaching 0. So our answer is negative 1. So what we showed is that the integral from 0 to 1, natural log of x dx converges to negative 1. Why is it negative? Well, think about the graph of natural log. It goes like that, and it passes through 1. So what we found is that the area is actually equal to positive 1, but because it's below the x-axis, the integral gives us a negative 1. Okay, that's a good place to stop, so we will see you next time.